Good evening, and welcome to another episode of Thought Leaders, brought to you by Space Center Houston and UTMB Health. Tonight, we're reviewing lessons learned and their impact on NASA's future. I am Dr. Ronak Shah, Director of Aerospace Medicine at UTMB Health, and I'm delighted to introduce our distinguished panelist speakers. With the assistance of Frank Buzzard, William Rod Jones, and Captain Joe Kerwin, Thought Leaders will review knowledge gained from NASA's work on Skylab in the International Space Station and discuss its contributions to the development of the Gateway, the lunar outpost that will orbit the Moon to support NASA astronauts in their much-anticipated return. Astronaut and physician Dr. Joe Kerwin was the first American medical doctor to travel in space when he served as a member of the Skylab 2 mission in 1973. Skylab proved that humans could live and work in space for extended periods of time. Dr. Kerwin will share his insight into those significant Skylab findings. During his distinguished NASA career, Frank Buzzard served as Chief Engineer of the International Space Station and as the ISS Program Director and Senior System Integration Manager. The realities of life aboard the ISS will prove invaluable as NASA moves forward with its return to the Moon and mission to Mars. William Rod Jones is a manager of the Gateway Vehicle Systems Integration Office. Mr. Jones will explain how scientists are integrating both past successes and failures from the ISS and Skylab to ensure that Gateway's mission is accomplished. I am honored to introduce tonight's distinguished panel of speakers and that you have joined me to learn from these legends. I hope you enjoy the lecture.
Hello, I'm William T. Harris, President and CEO of Space Center Houston, a dynamic science and space exploration learning destination and nonprofit science center. We also have the privilege of serving as the official visitor center for NASA Johnson Space Center. We share the story of human space exploration, past, present, and future, with more than 1.25 million visitors annually from around the world. Thank you for joining Space Center Houston's Thought Leader Series program, Skylab to Gateway, Living in Space, presented by University of Texas Medical Branch. Our Thought Leader Series brings you space and science experts from across the country who provide insights and perspectives on space exploration. Space Center Houston offers robust learning experiences that enable you to be a part of NASA's mission. In addition to our extensive collections, you can experience new exhibits and live programming, so there's always something new. I'd like to invite you all to join Space Center Houston's Moon to Mars Festival presented by Welby. The festival offers the public access to the latest in space exploration, and it will take place June 9th to 12th here at Space Center Houston. It's the first annual Moon to Mars Festival celebrating NASA's Artemis program and innovations that will help us establish a sustainable human presence on the Moon. Enjoy a festival atmosphere with live music, indoor and outdoor activities, and delicious food and beverage provided by Wolfgang Puck Catering. You can purchase your tickets today at spacecenter.org. Now on with our program. From our first U.S. venture, Living in Space with Skylab, to building a permanent presence aboard the International Space Station, ingenuity, training, and teamwork have been essential to the success of any of our programs. Now, as we return to the Moon with Gateway, our new pathway to deep space exploration, these skills will unearth new discoveries that will transform our everyday lives. In today's discussion, we'll learn about space history and humanity's quest for knowledge. I'm delighted to welcome our panelists for Skylab to Gateway, Living in Space, presented by UTMB. Our first presenter is Dr. Joe Kerwin, who served as NASA Johnson Space Center's Science Pilot Astronaut for the Skylab 2 or SL2 mission. He was subsequently in charge of the on-orbit branch of the astronaut office, where he coordinated astronaut activity involving rendezvous, satellite deployment and retrieval, and other shuttle payload operations. Dr. Kerwin continued his leadership efforts and served as the Director of Space and Life Sciences at Johnson Space Center from 1984 to 1987. He received a Bachelor of Arts degree in philosophy from the College of the Holy Cross in Worcester, Massachusetts in 1953. He then went on to earn a Doctor of Medicine degree from Northwestern University Feinberg School of Medicine in Chicago, Illinois in 1957, and attended the United States Navy School of Aviation Medicine in Pensacola, Florida, and was designated a U.S. Navy flight surgeon in 1958. Our second presenter, Frank Buzzard, spent a distinguished 30-year career at NASA Johnson Space Center, retiring in 2003 after leading the NASA Columbia Accident Investigation Task Force. He then served as Barrios Technology Incorporated Program Manager for the International Space Station Mission Integration Contract from 2003 to 2005. During his NASA career, Frank served as Chief Engineer of the Space Shuttle Program, Chief Engineer of the ISS, and ISS Program Director Senior Systems Integration Manager at NASA headquarters in Washington, D.C. He received the NASA Distinguished Service and Exceptional Service Awards for his contributions. Prior to Frank's NASA career, he served as a U.S. Army helicopter pilot for 5 years, including a Vietnam combat tour as a Chinook pilot and the 101st Airborne Division. He holds a Bachelor of Science degree in Aerospace Engineering from the University of Colorado and a Master of Science degree in Physical Science from the University of Houston. Our third panelist, William Rod Jones, is the Gateway Program Vehicle Systems Integration Manager at NASA Johnson Space Center. Rod has over 35 years of experience in space station design and operations. He was involved in all aspects of the program, including initial formulation and requirements definition, manufacturing, testing, on-orbit assembly, and sustained operations of the International Space Station. Rod began his career in 1984 at Johnson Space Center after completing his Bachelor of Architecture degree at Virginia Polytech Institute and State University. He served in the Human Health and Performance Directorate at Johnson Space Center, defining architectural design requirements for spacecraft, human factors requirements, crew equipment, and has held key management positions in the ISS program, including vehicle systems, pressurized elements, mission integration and operations, research integration in avionics, and software management. Welcome to all our panelists. What an amazing resume you all have, and you've all contributed so much. We're going to begin our program with brief remarks from each of our panelists, starting with Dr. Joe Kerwin.
Is it my turn? I guess it is. And it's my turn to talk about Skylab, which is the first and oldest program that we'll be talking about today. Just as I arrived at the Manned Spacecraft Center in 1965, people in NASA headquarters and at the centers were in the background discussing what to do after a successful Apollo program. Now, even before that, Wernher von Braun, who was director at the Marshall Space Center, had been an active speaker on the space program in the 1950s. He filmed movies with Walt Disney Incorporated and published a big article in one of the magazines. And his view, his vision for the program was first we learn how to go into orbit, then we do a space station, and finally, when that's all done, we go to the moon in about the year 2000. Well, President Kennedy took care of that in 1961 when he announced that we were going to go to the moon and return in this decade. And what a program that was. But we had to continue the exploration on, and we were going to have to do it with a considerably lower budget than the Apollo budget, which reached 5% of the total national budget in about 1967. So the thing to do, so thought von Braun and others, was to revert to the space station idea and to use existing Apollo hardware to do a prototype space station using, in fact, the fuel tank of the third stage of the mighty Saturn V rocket, the S-4B, and outfitting it as a space station. The early idea was to fly an S-4B on a small rocket, use the stage as a propulsion stage, and then empty out the fuel and oxygen and backfill with the stuff you needed to do a space station. A little testing convinced everybody that that was virtually impossible to do. Fortunately, one of the few good effects of canceling the last 3 Apollo missions, 18, 19, and 20, which was done, I think, partly for budgetary and partly for safety reasons, was that a Saturn V became available to this new space station program, which came to be called Skylab. And so down at Huntsville, they started planning how to outfit the Skylab and fully assembled, launch it on a Saturn V as a medical laboratory, a hotel, we called it the von Braun Hilton, with lots of storage for 3 long-duration flights by 3 astronauts each. They added a module for docking, for spacewalks, for Earth-looking cameras, a serious Earth observation program, and a module tacked onto the side for solar cameras, which became our finest science program. And put all that together, and why were we doing it? We were doing it to learn long duration flight first, and the primary objective of Skylab was the medical objective, to certify that human beings could live, prosper, and work hard and successfully for long enough durations that it would open us up to building a space station. And so we plan to launch 3 separate command service modules. First one for 30 days, the second for 60, and the third at first also for 60 days, because we needed 9 crew members to get a statistically good sample of succeeding in flight. And why were people nervous about that? We were about a year away from launching Skylab when the Soviet Union launched a spacecraft that stayed aloft for, I think, about 26 days with Russian cosmonauts. And when the cosmonauts then separated from that mini station and came home, they were all dead. And some people at NASA panicked. Some of the scientists went to Congress and said, "You've got to stop Skylab. Obviously, we have a serious problem." And those of us who were working on Skylab said, "This is dumb. It had to be something other than physiological." But anyway, it made everybody very nervous, or a little bit nervous anyway, when Skylab launched. And for the first time, we got to do good medical experiments for long durations on humans. So that was the primary medical mission. And of course, we added all the secondary missions: do good science, do good Earth observations, do good solar observations, build systems that are needed for long duration flight, for life support, for meals, and all of that. Just to say that in summary, we flew 30 days, we flew 56 days, we flew an 84-day mission at the end because the others had gone so well. We learned how to exercise better. We learned to eat more. And the third crew at 90 days came out in better shape. One of them actually gained a pound than the first and second crews. So we were able to say to Mr. Reagan at the end of that program, yes, human beings can work effectively for at least 3 months, and extrapolate that. We can do science, and we can have a permanent presence in space.
Just fascinating. Thank you so much. I'm looking forward to asking a number of questions about Skylab. I've written down quite a few things, but now I'd like to turn it over to our second speaker, Frank Buzzard, who will speak a little bit about his experiences. Frank.
I had the great privilege of working with a wonderful team of 16 nations to build the International Space Station. And as Dr. Joe Kerwin so properly pointed out, Skylab led the way and proved that we humans could spend long periods of time in low Earth orbit and in zero gravity. It does have debilitating effects on the human body, and we learned that we had to have exercise equipment on the International Space Station. And each astronaut in zero gravity can spend several hours a day, up to 2 hours per day, to do exercise to keep the cardiovascular system from deteriorating and to try to prevent calcium loss from the major bones. And that is always going to be a problem in zero gravity. So we began the International Space Station. Of course, I served as for a number of years, 15 years in the space shuttle program. And Space Shuttle was designed to be the big cargo truck that could build von Braun and NASA's dream of a space station in low Earth orbit. And we had the ability to assemble large pieces we would carry in the space shuttle. It required the robotic arm provided by Canada on the space shuttle to be able to assemble each module. It also required an airlock on the space shuttle so that our astronauts could get in their spacesuits and go outside and hook up cables, hook up fluids, and a number of different ways to activate each of the individual pieces that we sent up. It took many, many shuttle missions. It took many, many hours of spacewalks. We call them EVA, extravehicular activity, where the astronauts go outside and work in their spacesuits. All of that was practiced over and over and over again, the assembly parts and spacewalks in the neutral buoyancy facility, the largest swimming pool on Earth. We had learned on the Gemini program that spacewalks required simulation, and it required handholds and foot restraints, or you quickly can exhaust yourself. So those lessons from Mercury, Gemini, Apollo, and Skylab all transferred into building the International Space Station. The other thing I would comment on about the International Space Station is it is a collaboration and cooperation and partnership between 16 nations. And I would say that any future exploration, going back to the moon, going on to Mars, should indeed be an international effort so that the whole world can be participating in space exploration. So we built the space station, and we've had permanent presence in low Earth orbit for well over 20 years now. And we have learned the techniques of how to keep the body healthy for long periods of time. Right now, the next steps going back to the moon will be discussed by my dear colleague, Rod Jones, that I worked with for many years on the International Space Station.
Great, Frank. Thank you so much for that background. Now we'll hear from Rod Jones. Rod.
Early in my career, I became interested in architecture and its application to spacecraft and space stations. And I was fortunate enough to join NASA in the early 80s when space station design was taking off. And so we started to look at what were the design drivers and the important aspects of space vehicles for humans and science. And the things we saw repeatedly reoccurring in Skylab and Shuttle and the space station was the need for sustainability, affordability, of course, safety, and habitability. And these features all make the spacecraft more useful and more available to conduct long-term science. So what we've learned from the previous programs we've discussed for Dr. Kerwin and Frank Buzzard is that we need to have longer missions in space. They need to be affordable and they need to be sustainable. And so the Gateway program has learned and leveraging off all of the lessons learned from these previous programs. The Apollo program, the first mission was only 2.5 hours on the lunar surface. And so you had this large rocket, 6 million plus pounds of rocket and people and supplies, and the only thing reusable at the end of that mission was the crew on board. With ISS, we learned from Skylab that we needed to make it sustainable, so we created a transportation system that could resupply it affordably. Because Skylab was designed for a very limited mission, and we realized we needed spacecraft to be sustainable in space. And to do that, you had to have reliable transportation and ways in which the crew could actually work and repair these spacecraft while they're living in them. So what Gateway's goal is to be an integral part of a transportation system for Artemis. It acts as a transportation node permanently orbiting the moon. And its orbit is unique. It's a near rectilinear halo orbit, and it allows us to bring two transportation systems together. The Orion can dock to the Gateway orbit when it's furthest away from the moon, 70,000 kilometers, and then ride the Gateway into low lunar orbit, where the crew can transfer into a lunar lander and drop off the Gateway or undock and land on the lunar surface. And then that Gateway goes around the moon, orbits the moon, and comes back in 7 days to pick them back up. It's by breaking the transportation system up that we create a sustainable exploration capability. So that's the primary goal of the Gateway, to act as this transportation hub or node.
Wow, well, thank you all for those fascinating remarks about Skylab, ISS, and Gateway. And it's really amazing how we're building on knowledge and moving forward. But I want to go back in time because, Joe, you said something that caught my attention around the cosmonauts who lost their lives. Was it ever revealed why they didn't survive after their mission in space on Salyut?
Yes, it was revealed rather promptly. Actually, within a few weeks, we found that when the Russian spacecraft separated from their mini station, the hatch blew open. They lost pressure, and they all died of asphyxiation. So it wasn't the effect of long duration spaceflight at all. It was an accident with the hatch.
Oh, how horrible! This sounds terrible.
A tragedy, but a reassurance to us in a sense.
Mm-hmm. So was the Saturn V rocket the vehicle that then took the NASA astronauts on the subsequent Skylab missions? So there was one mission that actually brought Skylab to space, but for the subsequent transport to take the other crews, was it on a Saturn V vehicle, a modified?
That was a good point, and I missed it. The Saturn V was required only to put the big station, Skylab itself, into orbit. The 3 crew launches were done using that old S1B vehicle, which is a 2-stage vehicle instead of a 3-stage vehicle, more available, cheaper, and good to launch the command service module to where it could dock with Skylab.
Well, thank you. I think in all that I've read, there's not a lot of conversation about how we knew Skylab got up there with the Saturn V, but not how the crews got up there and came back again. So thank you for answering that question. I've been wanting to ask someone that for a very long time.
Excellent. And the CSM also served as our ambulance when you think about it. If somebody got sick or had an accident or something, we had return to Earth capability right there.
So for those initial missions, what was prepared for food for the astronauts? Because I know there was a period of time with Apollo, they actually prepared food pellets. And then there are the famous stories of astronauts squirreling away food that they liked, in their uniforms and their spacesuits, their flight suits. What was the diet like for astronauts on Skylab?
Okay, here's a chance to say kudos to the nutritionists and engineers who designed the diet for Skylab, because they were under a lot of constraints. For one thing, all the food had to last through launch and up to a year in orbit in order to be eaten, because the resupply mission simply didn't have enough weight capability to serve up fresh food. So there really wasn't any fresh food, but they were very creative in making preserved food in cans, in squeeze jars, in various ways, so that we had a pretty good diet. And we were working on the constraint that this whole program was a big medical experiment, and we had to document every gram we ate. If we opened a can and didn't eat all of it, we had to weigh it and get all that data. And then everything that was excreted from us, urine and feces, was also saved, sampled, frozen in the case of the fecal material, and brought down. So it was a very complicated medical system, which, however, involved good food. The problem with the diet was that we had an experimenter, a renowned experimenter, who thought that the right way to do an intake and output experiment was to make everything absolutely constant across all the subjects. That meant Jack Losma, who weighed 230 or 40 pounds, big strong guy, had to eat the same diet as Alan Bean, who weighed about half that, okay? This was not satisfactory. And we fought that until we got the guys to actually sit us down for a week, measure how much we ate on the ground, and then give us that much in orbit, except the investigator insisted that orbit was going to be less demanding of calories than the ground. So he subtracted 300 calories from everybody's diet. And we were pretty hungry up there for that first mission. We ate almost all the sugar cookies that were in the overage. And fortunately, the second crew and the third crew, the problem was recognized and they were given enough to eat.
Oh, that's absolutely fascinating. Well, I know here at Space Center Houston, we have the trainer for Skylab that was used at Johnson Space Center. And I'm not sure if you've had a chance to go inside of it, but does the trainer more or less accurately represent what Skylab was like?
Yes, the trainer is excellent. That might be a set of backup flight hardware, or maybe it was our 1G training hardware, but it's very good, and it's got a couple of the guys suspended in it in that big open space that shows it very well.
Oh, that is absolutely fascinating. Well, thank you for your service and being a human guinea pig and helping us understand what's required for humans to be in space. Well, I wanted to transition with a question over to Frank and ask you what were some of the lessons learned from Skylab that were really important to the development of International Space Station and making it habitable for humans and also so that they could thrive as astronauts.
So one of the great lessons learned that the food preparation we learned throughout all of the human spaceflight missions, Mercury, Gemini, Apollo, but especially on Skylab, that our people in Houston at the Johnson Space Center who prepared all these meals were constantly getting more sophisticated. And freeze drying equipment and rehydration and the pleasantness required to spend of eating a meal in space was greatly enhanced during the International Space Station era based on lessons that we had learned, especially with Skylab. So the truth is each of our different programs, Apollo, Skylab, Shuttle, Station, we continued to stand on the shoulders of giants who learned and who implemented, were innovative, and provided a tremendous increase in habitability for long-duration space flights. We have had people on the International Space Station spend up to a year in orbit, and I think to spend that long, you had to have a more habitable and desirable place to live than we had on Skylab. But all of those lessons that we learned were transferred, and we continue to do that, and we will continue to do that to build Gateway and then to go on to Mars as an international community, in my opinion.
So Frank, I have a follow-up question because it's very interesting. I understand with Skylab, they took advantage of the dimensions of the Saturn V rocket, right? Because the Skylab is actually quite large when you see the interior of it. And then what was the determinant for the volume of space for the International Space Station? Did it have to do with the possibilities of shuttle, how large that payload bay could be, or what determined the size of ISS?
Well, there are two things. One is the size of the cargo bay on the space shuttle, which was 15 feet in diameter and 60 feet long. We could put payloads in there. The second driving factor is how much weight or mass can you lift to 51.6 degree inclination, which is higher so that the Russian launch sites could launch things to the space station. That's about 45,000 pounds on the shuttle. So we could, those two things drove the size of each individual module. But from once Space Station Freedom was redesigned to include, during the Clinton years, to include Russia, our Cold War enemy, I guess. And then we determined that the living space that we wanted to have could accommodate 6 astronauts all of the time once we were fully assembled at assembly complete. So we have about 1 million pounds of International Space Station in orbit. And it has a pressurized volume when you add all of the pieces together, equivalent to the fuselage of a 747. So there's a lot of room, a lot of space. We wanted to have extra space for science so that we could do meaningful work in space and not just have astronauts. So it's a combination of making them comfortable, living spaces, sleeping quarters, areas for privacy, etc. All of those things we learned on the Skylab program.
Wow, that is just fascinating. So is there a maximum size for the ISS? Because there is conversation of Axiom is adding a module. Recently, the Russians added another module. So is there a calculation as to how big the ISS could become?
There is an ultimate limit in our ability to control the International Space Station, but it was designed from the very beginning to be expandable and to allow you to add new capabilities as technology improves. Just like the Hubble Space Telescope was designed to be serviced by the space shuttle, and the instruments on board Hubble were upgraded 4 to 5 times. We wanted to use the same concept to make the International Space Station expandable and to be able to upgrade its technologies. So we won't add a significant amount to the International Space Station, but the Axiom modules, which eventually will detach because they're younger, they will last longer. We're able to accommodate that concept so that the Axiom space station will eventually detach and be serviceable as a space station in the same orbit that the International Space Station is in the future.
Just fascinating. Well, Rod, I wanted to turn to you and ask about Gateway, because my understanding is it's a slightly different architecture and intent from ISS. So could you, for our viewers, explain what are the goals of Gateway and how does it differ from the International Space Station?
I think Frank gave you an excellent overview of the driving goals for the ISS, and that was to be evolvable, to accommodate changes in mission, to be sustainable for a long time, long periods, and it's demonstrated that we've had people living in space since the year 2000, permanent presence in space. So once you have that kind of capability, that kind of routine access, you can really begin to understand the effects of microgravity on people and materials processing in general. So Gateway's goal, first and foremost, is a little bit different. It's a transportation node. So the Orion is a great vehicle for getting the crew from Earth to the moon, but it's not a great vehicle getting them to the lunar surface. It's really designed to get the crew back safely to Earth. And so you want another vehicle to get you to the lunar surface, just like an Apollo, they used a lunar lander. So we have a second vehicle, a lunar lander, that gets you to the lunar surface. But unlike Apollo, we want to reuse our components as much as possible. And the only way to do that is to have a location in space, an aggregation point, which we call the Gateway. So it acts as an integral part of the transportation system. So now that we have this platform that we're building, Gateway, we can also use it for a science platform. And that allows us to do long-term science all year round, even when the Gateway is not in use. That particular orbit that the Gateway is in is incredibly beneficial because you can change that orbit and access many different locations on the surface of the moon. So you can explore different regions of the moon from the same aggregation point. And that orbit is also useful for exploration because it represents a really great place in space where gravity is minimized, the effects of gravity is minimized, and you can aggregate bigger and larger vehicles so humans can ultimately assemble a craft that can go all the way to Mars and back. So it's a great, important step in the overall exploration strategy to create a location away from Earth's gravity and yet accessible near Earth where we can go to demonstrate and prove out the technologies that we need in relative safety of being close to Earth where we can get back quickly.
That is absolutely incredible. So are there, so that's the structure for Gateway. I know that we have private industry as well that's beginning to look at going to the moon directly as well. And so how will we get from Gateway to the lunar surface? How will that work?
So one of the commercial partners is to provide a lunar lander system, and there are various phases of that contract to enable that capability. But then primarily the goal is to have the lander launch uncrewed and dock to Gateway, and there it resides until the crew comes. And with the Orion system, docking to Gateway, transferring to the lander, and then undocking from Gateway and landing on the surface of the moon. Once they conduct their mission, however long that needs to be, they ascend back up in the lander to dock to Gateway, and they can leave the lander there, and in the future it can reside and be reused or refueled.
So essentially it's a sky elevator. So it's a way that the same vehicle will be used to go back and forth between.
It's been coined the Buc-ee's of lunar space.
That is absolutely fascinating. So with the Gateway, there'll be experiments that can take place on Gateway. Do you have a sense of some of the projects that are being proposed? Because it would be uncrewed for a period of time, and it would also is enabling us to go out into an area of space that we have not spent a lot of time, right, on the far side of the moon.
That's correct. The science right now that's being proposed focuses on understanding the natural environment. One of the things we need to understand is how does radiation affect not only humans, but also the equipment that we fly out there. It has a very important impact and effect on avionics and our command control systems, degradation of materials, and the overall operation of a spacecraft. And key to going to Mars or any destination beyond the moon is having highly reliable systems that you understand how they operate and can be sustained for those long missions. So many of our early experiments are just that, measuring the environment, understanding the effects on the equipment, running the life support equipment to see that we get the reliability we need and the serviceability out of the hardware. And of course, studying what happens to humans when we're away from the Earth, the protection of the Van Allen belts and out in the lunar space where we have cosmic radiation.
So this is that's a fascinating point, because I think that's a question I have for all three of you. We often talk here about the 5 ways space can kill you if you're a human in space. And of course, there are probably many more, but one of the biggest is radiation. Of course, you've got both cosmic and solar. What did we learn about radiation from Skylab and then International Space Station, where we've had humans living in its environment, not protected by Earth's atmosphere for up to a year? And how are we using that information to prepare for Gateway and having humans living on the moon?
Skylab didn't teach us a lot about radiation because we were in low Earth orbit. We were underneath the belts of radiation, and therefore pretty much protected. The crews, for instance, our crew got about 3 or 4 rads or REM of radiation on 28 days, and the larger crews maybe 10 REM. That's fairly trivial. It's when you get outside those radiation belts that the radiation threat becomes real. There is a threat on the surface of the moon the moon is normally free of radiation, but if a big solar flare and particle event hits while you're on the surface, you can be in serious trouble, and you're going to need 5 or 10 feet of lunar soil to protect you. And the other big place for a threat, of course, is on the way to Mars, when you're outside those radiation belts. And again, not only a large flare, but just the radiation environment against which you have very little protection is a threat and has to be considered carefully for Mars missions.
On the International Space Station, William, we actually have radiation monitoring equipment to try to help answer the question of what is the radiation environment, define that environment, and then try to provide shelters inside of the International Space Station where we have measured that you have the most protection from solar particles, from solar flares, or from cosmic rays. And of course, all of that information is being used to design the gateway. And we will continue to monitor radiation. It is very debilitating to the human body. There are cosmic rays come from extremely high energy, very, very fast moving particles. And when they impact the human body, they can actually do some local damage, and they can also affect the DNA in the reproductive system. So we want to be very careful and understand that. Space station has been very helpful to better define that environment. And as Dr. Kerwin mentions, the International Space Station is below the Van Allen radiation belts, which are surround the Earth, and they're built from capturing these external particles, solar and cosmic rays. So when we go between the surface of the Earth or from low Earth orbit to the moon, when we carry people, we want to transition through those Van Allen radiation belts very quickly. We don't have to do that to carry cargo, for example. So I envision in the future that in low Earth orbit, the space station or its replacement in the future, a commercial space station, will be a transportation node along the lines of St. Louis when we went west, where we used the existing water transportation method to build our supplies, to build the wagon trains, and to provide them all they needed for a 4 or 5 month journey from Independence, Missouri, or St. Louis, Missouri, to the west. And I think that we will do a similar thing in low Earth orbit, making a St. Louis-like space station. And we will base a highly efficient transportation tug, if you will, to go from low Earth orbit to Gateway and back to low Earth orbit. We'll refuel it. It'll be 8 to 10 times more efficient than chemical propulsion, because cargo and resupply is a big deal at the moon or on the way to Mars. So we need to have a more efficient way to get the supplies people need to live on the moon, work on the moon, and at Gateway.
So Gateway is in the initial planning of that operational phase. But we will be following the same process Orion does. Orion has receives an alert, most likely from the ground, that says that there's been an event they need to protect for. And they have specific configurations that they've studied where they position all their movable equipment to try to create a type of a shelter, a fallout shelter, so to speak. And we'll be following that same practice. And until we understand more about the effects and the actual environment and the frequency of that environment and its impact on the crew and operations. We'll be practicing and having those kinds of operational measures put in place to protect the crew as much as possible. And that's really where we're at this point. So maintaining sensors in space, watching for these events, detecting them at the source or at the gateway itself, and the crew building shelters out of the equipment that we have, optimizing it for shielding. That's our basic plan.
So I'm curious, because all of you, this is related to the research and work that you're doing. It sounds as though that the habitat humans will be living in when they're on the surface of the moon needs to be below the surface, or it needs to have some kind of structure that provides protection from radiation and potentially from a direct hit from the sun. Is that the case? What will the nature of that structure need to be?
I think that it will require at least part of it to be protected, and lunar soil is the locally available effective way to do it. The whole base doesn't have to be protected that way, but you have to have some place to go if a big flare comes your way.
One of the advantages of being on the lunar surface is that you're on the surface. Out in space, you're bombarded from all directions. So on the surface, you've cut your risk exposure down significantly. So that's a good starting point. And then from there, you try to build on that protection by creating structures around you, above you, to deal with the rest of the radiation. Again, things that we'll have to learn how to deal with in space as we learn more about the environment and its effect on us.
And we are learning from the International Space Station that you must have an area that you might call a fallout shelter to protect you from radiation for some period of time. And so when we design a vehicle to go to Mars, where you're exposed for 8 months, for example, part of that architectural design may involve surrounding some part of the spacecraft with something like water that is an excellent absorber of these high energy particles. And you would have an area that you have tanks like a donut around your Mars transfer ship that can have either the fuel or the water or something like that that can help absorb that radiation.
That is so fascinating, because it hadn't occurred to me that equipment could be affected by radiation. And that could be catastrophic, right? If your equipment is not functioning well as a consequence. So I'm curious, what are there lessons that we've learned from this that are applied to us here on Earth that are helping us to keep ourselves more healthy and well from the preparations for sending humans into deep space? I know many of the experiments on the International Space Station, I think there have been thousands that have taken place over the last couple of decades. Do you all have any kind of favorites in terms of research insights that are now benefiting life for all of us residing at, all of us Earth dwellers who are here and may not be going into space?
I've been retired for quite a while, and I'm not up to speed on everything that's happened on the International Space Station. But I think that the major benefit of the medical research to Earth has been less the physiology and more the technology. We certainly started out by providing better telemetry of physiology to the Earth from the earlier spacecraft than we had before, and I think that the computer technology has aided medical diagnosis, medical interventions to a considerable degree.
One thing that I found to be personally very useful was early in the Apollo program and during the ISS, we have always been concerned about how might you be able to support medically on an International Space Station, for example, or at a gateway. Could you do surgery remotely? And so NASA funded some studies like that have now led to what's called the Da Vinci, robotic surgical system. And last year I had to have an emergency gallbladder removal. They put 4 little tiny 1/2 inch holes instead of cutting me from stem to stern. And a surgeon was able to manipulate these devices that would go in there that allow him to see, allow him to suture, allow him to remove. And the recovery period, because the damage to the human body is much, much less, it was absolutely complete revolution from previous gallbladder surgeries 20 or 30 years ago. So that is an example of how do we deal with helping humans live in space. And you will have to do that remotely on a vehicle that's going to the Mars or people that are living on the moon. And so there's an example. Another example of how space station has helped in technology development. Rod mentioned that sustainability and reliability is absolutely crucial. And we have learned on the International Space Station by doing sequential experiments to improve our ability to reuse air, to reuse water, including purifying urine, to make it completely drinkable. And those systems are complex. We've learned that they have to have special filters. They need certain maintenance. And we have evolved that over 20 years that will greatly help reduce the amount of air, nitrogen, water, etc., that we have to provide as cargo. And cargo to space is $10,000 a pound. Water weighs 8.5 pounds per gallon. So that using 1 gallon of water and being able to, on the space station, to take the humidity out of the air and turn it into usable water, and to take some water that I might not want to drink, but I can electrically create oxygen from that. So these experiments are helping make more efficient and more reliable systems that will help us continue to explore the solar system.
I would just say that what amazes me is the adaptability of humans to move from a gravity environment to a microgravity environment. Skylab showed we could live long periods of time in space. Space Station has taken that and extrapolated it out up to a year. And the more you learn about what happens to people in space, the more you learn about why they are the way on one gravity. We all evolved as a species in one gravity. And when you take that away, other forces dominate, osmosis, diffusion. It becomes very interesting to see how that affects the systems in the human body and tells you more about the bodies we have here on Earth. So I think we learn both ways. We learn by going into space to figure out how to project and explore into space further and stay there longer and longer, and likewise, bringing that knowledge back and improving our lives here on Earth.
Well, this next question is a little bit in the sci-fi realm. Is here and get that comment, but eventually we are looking at a future when humans may reside on other celestial bodies, right? We're talking about potentially Mars, making it habitable for long term, and we may procreate. So could this potentially accelerate our evolution if we're in these environments in which humans traditionally have not evolved, have not been in over time? So I'm surmising entirely, but so I'm just kind of curious what your thoughts are on this, because there is a lot of conversation about humans in the future becoming a multi-planet species. And if we are in different environments and we are highly adaptable, and we do, mutate and evolve, could that be accelerated by being in these environments that are radically different from where we have come from?
Wow. I don't know. The science fiction, I used to read a lot of science fiction when I was a kid, and the trips to other planets on other stars always involved multiple generations. it wouldn't be you that made it to this wonderful planet. It would be your grandson or your great-grandson. And the traveling of a ship that you have put together, which is a miniature state or nation, if you will, through multiple generations until someone came out the other end and landed on a planet that was different. Now, whether your body changed in significant ways genealogically during the trip, I have no idea.
I think evolution takes much, much longer than we are going to see in any short period of time that, say, humans living on Mars and having multiple generations on Mars. I believe that there will be a process that their body becomes better conditioned to. The gravity on Mars is 1/4 of what it is here on Earth, but that's going to take a long period of time. The other thing that occurs to me, that if you remember Stanley Kubrick's movie 2001, A Space Odyssey, in the 1960s, when he postulated that there was a circular wheel that was a space station in orbit, and that spinning wheel provided artificial gravity that would significantly reduce the debilitating effects that we see for long-term exposure to zero gravity. Loss of 20-25% of your calcium and we have tried to mitigate that by exercise equipment. But I think that in the future, for these long durations, we're going to have to spin vehicles and recognize that's the best way to prevent deterioration of the human body, and use centripetal force as some substitute, a third, fourth, maybe up to a half of Earth gravity to really help us be able to go on into the solar system.
Frank, that's a great idea and a great subject. And even back during Skylab, there was a group that wanted to fly a second Skylab vehicle and rotate it so that at the outer ends of the vehicle, especially in the sleep compartments and all, you could experiment with artificial gravity. The only earthbound experiments that I know of that are really good were done by Ashton Graybill in the Navy back in the 50s and 60s. He had a slow rotating room, and he found that people could adjust to the rotation aspects of the room up to about 5 RPM. 2 RPM was pretty easy for everybody. 5 RPM, you'd get kind of sick, but you'd get used to it. 10 RPM, forget it. So if you wanted to do artificial gravity, say on the way to Mars, you'd want a spacecraft long enough so that you could rotate it up to Mars gravity, let's say 0.4 G, without exceeding 2 RPM so that people wouldn't get sick. And it's a great idea, but it's kind of expensive. And I'm not sure whether we'll do it or not.
Wow, that is absolutely fascinating. To even think that there could even be a theory that could enable us to create some type of gravity, because you're right, in sci-fi they often talk about creating some kind of artificial gravity so that people seem oriented the way we are. So I'm curious, Arad, if you have any thoughts about this, if radiation could, and then especially for these long duration flights, cause changes to us over time.
Well, that's way outside my area. I'm a designer. I think, to me, the important thing is taking the next steps, right? I mean, we need to go to the moon in order to test the equipment, test ourselves, and have lunar exploration as a part of what we do. I think everyone on this event who joins it and watches it believes that the humans are destined to explore. That's what we do. And where that takes us, I don't think any of us can totally predict. But I think the important thing is to take that next step. And that's why we're here today.
Yeah, you reminded me to say something more about that. I'm very interested in the effect of lunar gravity for long periods of time and of Martian gravity when we get there for long periods of time. It may be that on the moon at 1/6 gravity, after a month or two, you're not nearly as deconditioned as you are in 0 gravity. There may be a threshold there. Interesting and very practical to find out.
That's actually an excellent question because, for example, we are involved here at Space Center Houston. We actually have a qualification in IRB, and we've been collaborating with Baylor School of Medicine and also with Johns Hopkins, and we're doing vestibular research with our guests around determining what is normal. And everyone is slightly different. And we know that, astronauts, some of them adapt pretty quickly to microgravity, and when they come back again, and others don't. And so there doesn't seem to be any kind of predictive factors. It's very individual. So we're trying to really build that data of kind of a variety of humans and what is considered kind of normal with their balance, and also vision and how vision can be affected by microgravity. So there are a lot of wildcards out there for humans to be able to go in space and keep healthy and well and thrive, and also be productive as investigators. This has been an absolutely fascinating conversation with all of you, and we're getting close to the end of our time, but I wanted to ask you each if you would just kind of share your aspiration for the future. You each are incredibly accomplished and have amazing experiences, and this has been an incredible conversation, but I'm wondering for our viewers today, what your hopes are for the future, and what your hopes are that space exploration might provide for us for future generations.
Well, I'd love to watch that first crewed spacecraft. I don't mean crude like crude oil, I mean with a crew in it, headed for Mars. At my age, I don't think I'm going to make it, but I'd sure love to do it. And then, if it's okay with you, I'd like to spend 2 minutes on one more aspect of Skylab that I didn't talk about, and that was spacewalking. It was EVA, and it was EVA done for the purposes of important repair. We had an airlock on Skylab, and we could do a spacewalk, but the only reason it was there was to get the old film from the solar cameras out and put new film in. There was never a whisper of talk about our ability to repair failures that occurred outside the spacecraft. And as a lot of you know, we lost a solar panel and a heat shield during launch on Skylab. We were able to replace the heat shield on our flight, the first flight, from within, but pulling up the other solar panel, which was stuck down, required us to do EVA without preparing the ground. And I think we broke open an area that has been thoroughly explored and improved on by the shuttle and the International Space Station, so that kind of EVA is now routine.
Yeah, I can confirm that based on all the lessons we learned from that mission and the ISS missions, the contingency EVA missions. We're planning for EVA on Gateway, even though we don't believe we need one. We believe we need to have that capability available. And so it's absolutely a fundamental capability we built into our spacecraft.
And we learned on the International Space Station how important maintenance and the ability to repair things is, and that requires a human to go outside in many cases. I'll give you one example. When we deployed one of the solar panels, the cable that deploys the big solar panel came off of a pulley, and we understood that, and it started to tear the solar cell. So we stopped everything. We did a planning session. How can we go repair this? And we had astronauts go out and use the robot arm where they had a platform that they were stable, could work. And he actually sewed together part of that solar panel and then put the cable back on the pulley so that we could continue to deploy that solar panel and generate huge amounts of power. So Skylab did the same thing, but the planning that we learned from Skylab to fix and release a solar panel to get more power, and to put a shade out that would reduce the thermal load inside, was all planned and certified, and new hardware carried up on the first Skylab crewed mission inside the command and service module, and deployed that Joe so properly talked about. Absolutely vital and important that you have the ability to go outside. But what we learned from Skylab that we applied to the space station is, to do these jobs outside, you must have handholds, the ability to get there, and you must be restrained. You have to put your foot in something that will hold you, either on a robotic arm. So we planned for that on the space station, and in future places like Gateway, they will take that and be able to provide these translation paths and the ability to secure yourself to do any work in space. So again, space station stood on the shoulders of giants, and we learned how to practice EVAs and spacewalks and do repairs on the ground in the big swimming pool. And we learned how important it is to pre-plan the ability to go outside and get to places you might need to repair.
Wow, well, thank you all so much for a fascinating conversation. I learned a lot today, and thank you all for your incredible service in advancing human space exploration. So again, want to express my heartfelt thanks to Dr. Joe Kerwin, Frank Buzzard, and Rod Jones for having a conversation with us today and helping to inform our viewers about the incredible innovations that they've helped make possible in exploration and continue to make possible as we prepare to return to the moon. So thank you all for tuning in today for our Thought Leader program, and we look forward to welcoming you here at Space Center Houston and our upcoming Moon to Mars Festival.